Hi, Gaurav. My name is Ross, and I hope I can help you with your series problem here. There's a lot that goes into it. I'll do my best to explain each piece. Starting off with just the basic scenario. So with my beautiful picture here, Kierra's dropping her ball 264 feet, and she estimates that it's coming up to 2/3 of its previous height after each bounce. So it's going to come up to 2/3 of 264, then go back down, and then 2/3 of whatever that is, and come back down, and that'll repeat over and over until the ball stops. So a couple of important things to keep in mind here as we start the problem. Number one is that obviously the ball is going to stop eventually. We know that. But based on Kierra's estimate, taking 2/3 of a number will never actually mathematically get you to zero. Take, 2/3 of 100, for example. If you just keep taking 2/3, you're just going to get tiny and tinier and tinier numbers, which is why we need this infinite series. So that's a huge part of this problem. Also important to note is just the fact that we have these pairs of arrows. So just keep in mind that we're going to have to double up on some of these distances, almost all of these distances, in order to get the total distance that the ball's bouncing or the ball's traveling, like the problem asked. So just keep in mind that kind of doubling up of those values as we keep going. All right, so just to get us into starting to write the series, let's start to think about how far the ball is going. So starting off with just the first 264 feet that the ball travels, it's falling to the ground. And then the ball is going to come back up, that's the second arrow, to 2/3 of that 264 feet, or that's what Kierra is estimating. Okay, now I am on purpose not evaluating that because in these series problems, often you're going to try and find a pattern with these different fractions that you're seeing. So I do not care what 2/3 of 264 is. I don't want to know. Not yet, at least. All right, and then for this next down arrow, it's actually going to be that exact same thing. So 2/3 of 264 again gets the ball back to the ground. Now here's where we're hopefully going to start to notice some patterns. Back down now to this next up arrow, the ball should be bouncing to 2/3 of the most recent height. The most recent height was 2/3 of 264. And again, I don't care what number that is, but I do care that my next height, this purple arrow, is going to be 2/3 of 2/3 of 264. So it's 2/3 of the most recent height. And again, I don't care what number that is. What I care about is the pattern that's showing up. And then again, since it needs to go back down that same distance, I need to add on that exact same number. So that'll get us back down to the ground. And then you maybe can already see the pattern here, but just to prove the point, I'm going to go ahead one more time. Let's do this next up arrow. And that distance, again, should be 2/3 of the most recent height, which was this guy. So I'm going to take 2/3 of 2/3 of 2/3 of 264. I'm just taking the last distance and multiplying it all by 2/3. And then to get us back down to the ground, I would take that same exact value and add it on again. And this process would repeat over and over and over infinitely. I'm just going to put some ellipses here, dot, dot, dot. Because again, just numerically, we're never going to get to zero. So we'd have to sit here doing this for the rest of our lives and we'd still not be done. So this is where we try to find some patterns and turn this into a series that we can evaluate. So let's look at some patterns that we noticed already. Number one, like I mentioned earlier, just about every one of these values has a partner, it has a twin. So we have these two match up, the purples, the reds, et cetera, et cetera. The only odd man out is this 264. But for the ease of it, for now, I'm going to pretend that 264 also has a partner. So I'm going to add on a 264 up here, just so that pattern will apply to every number. And I just got to remember at the end to take that extra 264 out. But because of that, if I add on that extra 264, then what I can do is I can rewrite all of this by saying, okay, my distance is equal to 2 times, and then each one of these terms by itself. So 2 times 264 plus the first bounce, which would be 2/3 of 264. If I can get that to copy and paste. That guy, and then plus the next term, 2/3 of 2/3 of 264. And this guy down. Got an extra plus sign in there, but it'll be all right. And then plus the red one. So keep doing this over and over again. So it's basically the same thing, but it's at least a little easier to look at. We have fewer terms floating around. So instead of all of those things, we just have 2 times every single one of them. Get the 3 back in here. And still dot, dot, dot. All right, so now what other patterns can we notice here? Another thing that I notice is that I have a 2/3 popping up. In fact, multiple 2/3 in all of these. Not only that, but in this second term, I have 1 2/3 fraction. In this next one, I have 2. In this next one, I have 3. So I also have a way that I can rewrite this. I'm going to erase some of this stuff so to give myself some room. Let's get rid of all of this. Oop, Kierra went with it. She'll be all right. All right, so bringing this up to the top. Okay, so what I'm going to do is I'm going to rewrite this as 2 times 264 plus 2/3 times 264 plus, and instead of 2 of these, I'm just going to write 2/3 squared times 264 plus, and then there's 3 of them, so 2/3 cubed times 264. And hopefully you can notice the pattern that's going to keep going. Even without knowing the others, I can guess that the next term would be 2/3 to the 4th times 264. And now you maybe can see where this series is coming from, dot, dot, dot. Another step I can take, they all have a 264 involved. That's no accident. So I can actually factor out that 264. Remember, that means that I divide every single term by 264 and bring it to the outside. So that means I would have 2 times, the 2 is from the outside, 264 comes to the outside with it. And then left on the inside would be, well, 264 divided by itself would be 1 plus, and then dividing every one of these terms by 264 would just cancel those, which is super convenient because all I'm going to be left with now is these 2/3. So I'd have 2/3 plus 2/3 squared plus 2/3 cubed, et cetera, for infinity. All right, now there's one other little trick to see here, and it comes back to that idea of not everything matching, right? So just like a little while ago where we had almost everything with a partner and we put in the extra 264, we can't forget about that 264. Just like then, I have almost every term here in the parentheses with the 2/3. The only one that doesn't really fit is the 1. But let's think about what we have here. I have a 2/3 cubed. I have a 2/3 squared. I could even write this one as 2/3 to the 1st power, because putting something to the 1st power doesn't change it. So how could I rewrite this 1? This is a really common strategy in these types of problems. I'm going to rewrite the 2 times 264 out front. And I'm going to rewrite this 1 as 2/3 are key fraction to the 0 power. Because anything raised to the 0 power is the number 1. So I am perfectly allowed to rewrite the number 1 as 2/3 to the 0. And now that term matches everything else that I'm looking at. All right, so now we finally get to the point where we can write our series. And before we move on, just because I'm afraid I'm going to forget it, I'm going to make sure to put at the very end minus 264, just because I need to remember at the very end of this problem to get rid of that extra 264 I put in to help myself out. So now let's try and turn this into a series. Based on these values, what can I do here? Well, when I have a series, I want to have a pattern that I can follow. And so what I notice here, if I want an infinite series with a sum from n equals 0 to infinity, the common term I have, or the common ratio, is 2/3. I missed the first number. I need to put my 2 times 264 here first. 2 times 264 is 528, so I'm going to put that. And then I'm going to multiply by, not this entire sum of numbers, but instead I'm just going to put 2/3 to the n power. And so what that means is, n starts at 0. I would plug that in and get 0 first. That's this term. And then I would add on, n equals 1. That's the second term. And then add on, and then keep going and keep going. So this expression turns this entire, this whole thing into one easy to read sum. The only thing that's not here that I need to make sure to put on, again at the very end, is that minus 264 that needs to get taken out. So this is a whole, this expression takes care of the whole situation. If you could evaluate this, you would have the answer. You would have the total distance that the ball travels. The tricky part is, how do you figure out what this first part is equal to? I know I need to subtract 264, but from what? What number is this series equal to? Well, this is where the magic happens. This is where all of this stuff over here at the right-hand side comes in. This is a rule that you can use when you're dealing with convergent series. Convergent means that there is eventually a point when it stops, right? Like in our case, the ball eventually stops. And that only happens if, you can see this bottom piece, if the r in your formula is less than 1 but greater than -1, so the absolute value is less than 1. And in the formula, that r is our common ratio, which for us is the 2/3. So hopefully you can see that what we've written here matches the form of our formula. They're using k, we're using n, but it's the same difference. They have an a value here. Our a value is 528, and they have an r, a common ratio, being raised to their exponent. That number for us is the 2/3. And what this rule says is, if you have a converging series of that form, then you can rewrite it as a divided by 1 minus r. That whole series is equal to a over 1 minus r. So for us, that would be, and it's this negative 264 is not involved. So for us, our a is 528, so that would go on top. And then divided by 1 minus, and our r, the common ratio, is 2/3. And don't forget that 264 that needs to come off at the end. So weird looking 264. So now we almost have our answer. The series is gone, the sum is gone, we just have numbers to work with. So a little bit of arithmetic. 528 over 1 minus 2/3. 1 minus 2/3 is just a third. So 528 divided by 1/3, which is the same as 528 times 3, which is equal to 1,584. I'd love to say I did that in my head, but I did it earlier. And then the only other thing I need to do is make sure to subtract the 264. And when I do that, the final answer I get is 1,320 feet. So the last few steps are actually pretty quick and not super intense. The biggest piece of the puzzle, aside from just knowing this rule of turning a series into an easy fraction, is figuring out how to write the series in the first place, finding that pattern and figuring out how to write that series. So I know that's a lot of steps and a lot of info. I hope I explained it well enough, and I hope that this helps you to tackle additional problems like this in the future. So good luck, Gaurav.